Okay, I'd say we can start since we are enough. So welcome everyone. I'm Daniele Cinieri. I'm a developer and data scientist at Dot. And on behalf of all the OpenDot team, I want to say thank you for participating to this workshop. It's a pleasure to have you here. I have to remind you that this is a recorded session. So if you have problems with this, you can switch off your camera and you won't be recorded. So this workshop is about satellite data, or even better, Earth observation data. It will be, let's say, gentle introduction to this rather complex field in data processing. But it's also, at least to me, it's very fascinating. So it's definitely worth to investigate it. So let's see the agenda for today. Okay, we are introducing the workshop. Then there will be an overview of the Copernicus program and the Sentinel missions by Julika Wolf from ESA. She's here with us in the call. Thanks, Julika, for participating. We appreciate it a lot. Then we will go ahead with visualizing a phenomenon called the urban heat islands with a software developed by ESA, which was especially developed for processing data coming from the Sentinel satellites. And then we will go ahead with making more or less the same operations with Python. So we will first see an approach by using a graphical interface, and then we will instead dive a bit into coding and see how we can automate those tasks. And we will have probably a short pause at 11 and a quarter. And then we will go ahead with visualizing nitrogen dioxide urban concentrations. And we will use another source of data, which is Google Earth Engine. Finally, we will have, let's say, half an hour or a quarter of an hour for question and answers. Before starting, let me say a few words about us and the frame in which we have been able to host this workshop for free. The entire workshop series Climate Data is part of the Distributed Design Project, which has been founded by Creative Europe, a platform that acts as an exchange for talents to network and share skills and practices. OpenDot is part of this network along with other 15 partners from all around Europe. And let me also spend a few words about us. OpenDot is a research and open innovation hub. It is a place for learning. It's a place for prototyping, since we are a fab lab, and also for sharing. We are located in Milan. We're open to the public. And well, here in the image, you can see the typical stuff we make, but we also deal with software. We are very multidisciplinary. And OpenDot was founded by Dot, which is a multidisciplinary design studio. It's actually one of Italy's first work in the interactive design field. And so I'm actually from Dot, but today I'm here in behalf of OpenDot. Also, before starting, there's some material that is needed if you want to actively write code with me, or otherwise you can just follow me and take notes as you prefer. The complete package is quite heavy, I'd say. It's over 1 gigabyte. But that's because we have data, 1 week of data regarding Milan. And so that's why the package is that big. If you want, there's also a lighter package. It's around 200 megabytes. But there is no input data for the second part. So for the part we will do with Python, as you prefer. You can decide to download the full package and follow also the coding part actively, or you can just, I don't know, take notes and enjoy the presentation. Okay, so I'd say that we can go ahead by having an overview of the Copernicus program and the Sentinel missions. And as I said, it will be done by Julika Wolf. She's a graduate trainee at ESA. And so I'll leave the word to her.
Thank you, Daniela. Let me share my screen. I think you have, yeah, exactly. You have to stop screen sharing. Let me just pull you over. Okay. Can you see the presentation? Yes? No? Question mark?
Yes.
It's good? Okay, perfect. So yeah, nice to meet you all virtually. It's a bit of a pity we can't meet in person in Milan. Yeah, as Daniela already introduced me, I'm Julika Wolf. I'm originally from Germany, but I'm currently a trainee at ESA here in Italy in Frascati. And for the next roughly half an hour, I'm going to talk to you, or I'm going to give you an introduction on how you can basically use free and openly available satellite data to create visuals that tell a story on global change, especially focusing on the way that we as humans impact our planet. So what's the plan for today? First of all, I'm going to give you a little bit of a background on who I am or what the team I am part of is doing and what the FEE experience is, which is our main project here. Then I'm going to talk a bit about the Copernicus program, how it's structured. And I'm assuming that most of you don't have so much of a background in Earth observation, so I'm keeping it very broad. And then I will go more into detail about the Sentinel satellite family, which basically forms the core of the Copernicus program. But more about that later. And I will also introduce some of the satellites more in detail. And most of all, I'm going to show you some visualization examples that our team has made. And then lastly, I will just give you an overview of two different ways of accessing Sentinel data. One of them is the Copernicus Open Access Hub, and the other one is Google Earth Engine. And this is not an exhaustive list. Of course, there's different other platforms out there, but these are the two ones that you will be using later on with Daniela. So first of all, my background, I'm a YGT, it's called a Young Graduate Trainee at ESA, which is a 2-year program that I joined last October, a week before the second wave hit. So today, exceptionally, I'm actually in the office, which is nice. So my background is in physical geography, which means I feel like a scientist at heart, but I'm also having a passion of getting the science out there and creating easily understandable visuals for the non-scientific community. And yes, I'm at ESA, I'm working at in Frascati, which is basically ESA's Center for Earth Observation, also known as ESRIN, where I'm part of the FEE experience, which is ESA's visitor center for Earth observation, basically. And I'm on the one hand supporting the creation of new content here at the visitor center, especially focusing on global change and climate change in particular. But I'm also supporting the production of visuals for general communication activities for Earth observation. So for instance, if you go on the ESA website and you see really cool looking satellite images, they're, when in doubt and they look really cool, they're from our team. And our team is currently very small, comprised of 5 people. So what is the FEE experience? As I said, it's the visitor center or the multimedia center on Earth observation here in Frascati. And it's aimed at increasing awareness of ESA's Earth observation programs and applications. So it basically has two main aspects. You have the technical side, so we're trying to explain or increase understanding of Earth observation techniques and applications. But then in terms of content shown, we're also trying really to focus on things that show how humanity is impacting our planet. And we do this by showing 4 different thematic stations, allowing for different perspectives, basically ranging from local to global. And on the right, this image that you see here, this is one of the stations that we're having called the half globe, which is a almost 2 meter in diameter big half globe. And behind there, you have a huge projector, and it allows you to project all kinds of global data sets. And then you have this little ball here on the right in blue. I'm not sure if you can actually see my mouse, probably not, so I'm pointing for nothing. But anyways, you see this little blue dot here, and you can move and scroll around and look at different parts of Earth. So this is actually my favorite station of the 4. So let's delve right into Earth observation. So I'm going to start with this little overview slide, basically showing all of ESA's satellites that either have been in orbit here on the left, just above the globe, or are currently in orbit or will be in the future. And right now there are 16 different satellites in operation, but we're having 38 under development and 14 under preparation to be launched in the near future. And these all these satellites can be divided into 3 different types of Earth observation satellites. So on the left side, you have those that are really specifically designed for scientific purposes. They're also known as the Earth explorers. So for instance, you have IOLAS, which is designed to measure wind fields. So all of these are very specific, the ones in green. Then in the middle, you have the ones for the Copernicus program, which we're going to focus on today. And then on in orange on the right-hand side, you have the meteorological satellites. Okay. So what's the Copernicus program? It's basically, like you could say, it's the most ambitious Earth observation program out there right now. And it's the European Union's Earth observation program. And its aim is to monitor Earth and its environment for the benefit of European citizens. It's initiated and managed by the European Commission, but it has a lot of different European agencies that are involved in various different parts of the Earth observation program. And basically ESA oversees the development of the space segment. And the program is not entirely new. The first plan started over 20 years ago, but the Copernicus program, as it is operational today, and as we know, it started with the launch of Sentinel-1 in 2014. So how is this program structured? I made this little flowchart to illustrate this. And basically, as you can see on the left, the raw data comes from 2 different sources. We have the space component, but we also have an in situ component. And the space component is comprised of 2 different types of satellites. So we have the Sentinels, which I will talk about more later. And they are specifically designed for the Copernicus program. But then you also have the so-called contributing missions, which were either already up there or are part of different programs by other space agencies, but they act in a complementary way. And then the second part of the data is the in situ component, which is acquired by different sensors or weather stations. And then this is data that serves as calibration or validation material for the space component. These 2 data are then fed into the so-called Copernicus Information Service, which processes and transforms it into a way that you can actually use it as the end user, so into useful information. And most importantly, this type of product is then free and openly available for everyone. So the Copernicus Information Service, the one that was in the middle in this flowchart, is divided into 6 different areas, which are climate change, marine monitoring, atmosphere, land security, and emergency. So these have also all their own websites that you can check out later on and provide very different data sets. And today we will be working with the atmospheric and land monitoring services. And these are implemented by the European Center for Medium Range Weather Forecasts and the European Environmental Agency, respectively. So they are the agencies that, that process the data ready to be used. Okay, so the Sentinel missions basically form the core of the Copernicus space segment. As I already said, they're specifically designed for the needs of the Copernicus program. And so far, each mission consists of twin satellites that are simply called A and B. And they are basically just replica of each other. And the reason why we have twin satellites is that, yeah, we just want to ensure that we have a continuous data coming in and enough data coverage. But there's also several future high priority missions under development for data currently not covered yet. So let's talk about the Sentinels themselves. There's currently 6 of them. They're called just Sentinel 1 to 6, so quite easy to remember. And they all carry very different instruments on board depending on what they measure. I'm just going to talk very quickly about all 6 of them before we delve more into detail. So up here, the first one, Sentinel 1, which is a all-weather day and night radar mission. Then down below, you have Sentinel 2, which is a multispectral high-resolution imaging mission. What that means, you will see later. Then we have Sentinel 3, which is a larger satellite that carries multiple instruments at once. And then we've got Sentinel 4, which is not launched yet. It's the only one that is not launched yet of this list. But once it will be launched, it will be monitoring air quality specifically over Europe and North Africa at a high temporal resolution of every hour. And it's quite different from the first 3 Sentinels because those are at a so-called polar orbit, which means that they're flying from pole to pole and eventually they're covering everything of Earth. But Sentinel 4 will be in a geostationary orbit much further out, which allows it to always see the same spot on Earth. So you can only cover Europe and North Africa, but that allows you to have a very high temporal resolution. Excuse me, I'm going to just drink some water. And then next we have Sentinel 5P, where the P stands for precursor, and it's basically the forerunner of Sentinel 5. And that's it will also be, or it is monitoring air quality, but in this case, it's a global air quality monitoring mission and not just over Europe. And once Sentinel 5 is up, it will replace Sentinel 5P. And then lastly, we have our most recent addition, which is Sentinel 6, which is a radar altimetry mission designed to monitor changes in global sea levels. And Sentinel 6 was launched in November last year, so very freshly in orbit. And today we will be working with Sentinel 3 and Sentinel 5P data. So now let's get basically to the heart of this presentation, which are the satellite application examples that my team made in the past, either for communication activities on ESA's website or for our visitor-centered FE experience here. Let's start with Sentinel-1. Just as a recap, as I already mentioned, it's a radar mission. It carries a so-called C-band synthetic aperture radar as an instrument, which means that it is an active instrument that sends out radar pulses, which are then reflected from Earth's surface and bounced back and registered by the satellite sensor. And that can tell you all kinds of things about the surface. So you can, for instance, measure changes in surface height with it, or changes in surface roughness, which is basically surface texture. What is so special about radar is that it passes through clouds, and since it's an active instrument, it doesn't depend on sunlight, which means that you can obtain data all day and night and even in bad weather conditions, which makes it handy for various applications at the poles, for instance, where it's of course dark half of the year. So you can measure sea ice and icebergs, but also oil spills, and you have different land applications, and also it's also used for emergency management. So let's look at the first visualization as a little taster of what you can do with Sentinel-1, even though you won't be working with it today. And by the way, I made a little list that I sent to Daniela yesterday evening, where I also, those things that I'm showing you as visuals that are not from the FEE experience, but from the website, I just have the URL, and you can have a more detailed look at it later by yourself. So he can pass the list around. So this animation I'm going to show you is of Pine Island Glacier in the years 2014 to 2019. And it's a glacier that connects the West Antarctic ice sheet with the ocean. And it's been losing ice over the last 25 years. And ice velocity has increased. Let's hope that the internet connection is fast enough to play this. And as you can see, you can really see how dynamic the glacier is moving, and how at first huge ice chunks are breaking up, which are then in itself building all kinds of little icebergs. So on the one hand, it illustrates how dynamic this glacier is, but also it shows how important it is to have satellite data over an area that is so remote and dark for many months of the year. So the next illustration for Sentinel-1 data falls under the emergency management category. In this case, it's flood mapping after Cyclone Idai flooded Mozambique on the 19th of March 2020. And in case you don't know about Cyclone Idai, it was one of the worst tropical cyclones that hit Africa. And although, of course, it's difficult to link a single extreme event like this to global change or to climate change, it's likely that we're going to see more extreme precipitation events like this in the near future. So this is the image, and it's basically what you're seeing is a flood map here, where you see all the flooded areas in red around the city of Beira here on the right. And it's a multi-temporal image, which means that you need data from before the flood and after the flood, which you can then combine, and you can make use of the fact that when an area is flooded, you have a change in surface texture, which you then illustrate in red typically. And this also shows how important radar data is, because of course, when you have a flood, usually the area is completely covered in clouds. So you wouldn't be able to see this with just an optical instrument or a camera. And then the last example I'm having for Sentinel-1 is maybe a less well-known one. It's showing an oil spill just off the coast of Corsica in the Mediterranean that happened in October 2018 because of the collision of two ships. And as you can see here, this area that is circled in shows how you can nicely monitor basically marine pollution as a black smear. And the reason why you see this so well is because oil causes the wave motion to dampen down. So your surface gets smoother. So when the radar signal hits the ocean, it's more likely to be scattered away from your sensor. Hence you get less signal back and the area appears as darker. Okay, but let's now move on to Sentinel-2. As I mentioned, it's a multispectral imaging mission for land monitoring, and at a high resolution of 10 meters. And it's a passive instrument, which means that it basically senses solar radiation reflected from the surface, so it wouldn't work at night or when it's cloudy. So it works a bit similar as a camera would do, but the difference is that you can also observe parts of the electromagnetic spectrum, usually not measured by normal cameras, such as infrared. And it's used for a lot of different applications, but its main focus is land monitoring, such as forest management or agriculture. So for instance, you can use Sentinel-2 for forest fire monitoring, in this case showing forest fires that occurred in Oregon in September last year. But basically the entire West Coast at this point was almost on fire. But I liked this image because it illustrates a few different things. So what you can basically see is on the left hand, so it's the same acquisition, first of all, but on the left hand, we combined the red, green, and blue bands of the satellite to just create a normal natural color image, which really shows you the extent of the smoke. But then on the, that was on the left, sorry, and then on the right hand side, you have the same acquisition, but in this case, we're making a so-called false color composite. So you're creating an RGB image using the shortwave infrared bands, which allows you basically to go look through the smoke and see which area on the ground is burning and the extent of the forest fire instead of just looking at the smoke. What I also like about this image that it shows by chance the 4 reasons of deforestation, the 4 main reasons of global deforestation. On the one hand, of course, firstly, you have the forest fires, but then when you look down in this little corner here on the lower left corner, you see Eugene and you see urban sprawl as a second cause. Then you also can see agricultural expansion as a third cause. And then in the middle, you see these little squares, which is deforestation because of wood production as the 4th cause. And then the next one, also with Sentinel-2, is a little very simple animation showing the drought in California right now. And this is one that I made a few days ago, basically showing the area outside of LA in June last year versus June this year. And of course, for a scientific study, that wouldn't be very scientific to take one year and then the other and say, hey, climate change is happening. But in this case, I think it illustrates quite well how different or how much drier this year is in comparison to last year. So you do see in the upper part of the image, the area that is very white is a scar of a forest fire that happened last September. So after the first image was taken. But then you can also see this just all around the area is super dry, very brown, and the water reservoirs that are used to provide drinking water to LA are almost depleted. And basically you can create an image like this or an animation like this simply at home by downloading Sentinel-2 data and using the RGB channels, making an RGB image, and then like furbishing it up a little bit in Photoshop and adding annotations and making adjustments and so on. And then the last image of Sentinel-2 is even simpler. I think it just speaks for itself. It's just a RGB image over Borneo showing deforestation because of palm oil plantations. Okay, so enough of Sentinel-2. Let's move on to Sentinel-3. As I said, it's a larger satellite carrying multiple instruments, measuring various different things. So the first instrument or the first sensor is called OLCI. It's the Ocean and Land Color Instrument, which is an optical instrument a little bit similar to the one of Sentinel-2, but it provides a much, much bigger picture, although at a coarser resolution of 300 meters instead of 10 meters. And it's specifically useful to study ocean and land color. The second instrument is a sea and land surface temperature radiometer, the SLSTR instrument. And basically, as the name already suggests, it's used to monitor sea and land surface temperature. And this is also the one that we're going to use today. And then the third instrument, and not so interesting for you, is 2 altimetry instruments used to study sea surface topography. So the next illustration I'm going to show you is basically based on the data that you will be using today, namely level 2 processed land surface temperature. And in this case, we're showing the heat wave in Europe that happened in 2019 as a little GIF animation, where you basically just see within 1 month from June to July, temperatures really went up in all of Europe. And if you pay a closer look, you can, for instance, spot the Alps that are where snow is still persisting. You have these very cool blue or like colder blue areas. But then you can also already spot some urban heat islands, which are interesting for today's workshop. For instance, you can see that Paris is really, in the June image, much more red than the surrounding areas. or you can spot Munich in Germany and also the entire Po Valley, including Milan, is warmer than the surroundings. Then the next image I'm showing you for Sentinel-3 is a global sea surface temperature image. And this one we're also projecting on the half globe in the FEA experience. And we're having it as a full animation over several years, but I figured I shouldn't put too many animations in here because otherwise my presentation will be lagging a lot over Zoom, unfortunately. But I think even if you look at this still, which is from July 2020, you already see a lot of dynamics going on. So for instance, you can see when you look at the East Coast, just over Florida, East Coast of North America, you can see the Gulf Stream as this red line and then going over to Europe. You can also see right at the equator that it's a little bit less red because you have a lot of precipitation coming down. So it's slightly cooling off the sea surface temperature. Then if you look at the West Coast of South America, you can see that it's not an El Nino year because you have this colder band, otherwise it would be all red. And then also on the western sides of continents, you can see these blue stripes, for instance, here in Southern Africa, where you have so-called upwelling zones where cold and nutrient-rich deep water is welling up, and then that's really good for fishery. Okay, the next one is Sentinel 5P. Which is, as I said, the global air quality monitoring mission. And it carries an instrument called TROPOME, the tropospheric monitoring instrument, which is a spectrometer. And it measures various trace gases in the atmosphere, such as ozone, nitrogen dioxide, sulfur dioxide, carbon monoxide, formaldehyde, and methane. But it also provides daily data on clouds and aerosols. And as I said, it's a precursor mission that is aimed to reduce data gaps between Envisat, which used to be in orbit, an older satellite, until the launch of Sentinel-5. Okay, so, and that's one of the data sets that we will be working with today. So the next illustration, the next visual, maybe you've already seen it because it went pretty viral at that time, shows basically the impacts of the COVID-19 first lockdown on European air pollution. And it compares the spring nitrogen dioxide emissions in 2019 versus 2020. So nitrogen dioxide is an air pollutant that causes respiratory issues, and it's mainly emitted by the combustion of fossil fuels. And as people had to stay at home, you can see how like both road transport and industrial processes decreased, and so did pollution. For instance, over Milan and Paris, you see it a lot. Then my second image for Sentinel-5P is again a global data set for carbon monoxide, which is showing air pollution caused by forest fires. And it's again a data set that we are usually showing on our half globe, where you can see global carbon monoxide concentrations in August 2018 versus 2019. And one thing that you can spot right away is if you look at sub-Saharan Africa, that you have this big plume of carbon monoxide, which is always there in August because of seasonal biomass burning. But what you can also see is, for instance, in the Amazon in 2018, you had very little forest fires, whereas in 2019, you had a lot of fires. Hence, you have this big plume of carbon monoxide in 2019 over South America. And then lastly, we have Sentinel-6, which is the newest addition to the Sentinel family, launched in November last year as a radar altimetry mission. And its main purpose is to extend the legacy of already existing sea surface height measurements carried out by older satellites who are now reaching the end of their lifespan. So this is the last visual I'm showing you from my side, and it's basically a visualization of the data that Sentinel-6 will continue, namely the long-term trends in regional sea level trends, regional sea level. So in this case, you're seeing the annual average change in the years 1993 until 2019. And it's another data set that we're usually showing on our half globe, but in this case, it's like nicely already wrapped around the globe. And what it really shows is that sea level rise is really not uniform at all, but it's basically influenced by a lot of regional factors, such as local ocean currents and winds and all kinds of other factors. Okay, but how do you access all this data that I just showed you? So Daniele will talk about this much more in detail, but I will just give you a little overview of the two platforms. So on the one hand, we have the Copernicus Open Access Hub, which is also called the Sci-Hub. And this one provides you a complete and free access to all Sentinel user products. So there's different interfaces, but one of them is the Open Hub, which is the graphical user interface, as you can see by this little screenshot on the right. So you're basically just having a map, and then you can draw a little area of interest with a polygon, in this case over Rome, and search for some keywords like the ingestion date of the data or the satellite instrument. And you can then download the data, and all of this is for free after you registered an account. And then the second method, or the second platform, is via Google Earth Engine, which is my preferred way of doing it if I don't want to just have one single acquisition, but I want to have acquisitions over many years, for instance, for the animations. So Google Earth Engine is a cloud computing platform by Google that is designed for the analysis and visualization of various satellite and geospatial data sets. And the data catalog is stored on Google supercomputers. You don't have to download anything yourself. And it doesn't include the entire Sentinel data set, but it does include several Sentinel products. And you can access this by enabling your Google or Gmail account for Google Earth Engine. But you do need to have some knowledge of either JavaScript or Python for the scripting interface. So that's it from my side. If you have any questions, ask them now or write me an email later, however you want. And otherwise, enjoy the workshop. I will probably stick around for a little longer, depending. Maybe not the entire workshop, but let's see. Okay.
Thank you, Julika. Any questions for her?
Welcome.
Okay, I guess it was all clear. So thank you a lot again. It's been really important for us to have an introduction by you, also because the Copernicus program is very large, and to have such an overview with these examples, it's really clarifying. All the samples that you have seen, so the animations and the images, are also included in the package that I asked you to download. And you can see the original URLs to access them on the ESA websites. So before diving into the practical part, I would like to hear a bit from you. So just a short sentence to say who you are and why you are here, if you have any interesting project, okay, just to break the ice. I would say that I could just ask the first one, and then he or she can nominate someone else to do the same, okay? So I start with Angeles Briones.
You're muted.
You're muted, Angeles.
Thank you, sorry. Good morning, everyone. I am Angeles. I'm a researcher at Density Design at Politecnico di Milano. And I was super curious about this workshop because I'm also interested to see how can I use satellite imagery for doing research about missing people, specifically in Mexico. So I'm very curious to see how, from the visual and the data from the satellites, it could be put on practice for that type of research. So now I have to give the microphone to Miguel Ferretti.
Hi, everyone. Thank you, Angeles. I'm Michele. I'm a machine learning scientist at Booking.com by day, but today I'm here as a private person. And I also have a background actually in Earth observation. I did my bachelor in remote sensing at Unibicocca a lifetime ago. So I'm here actually to catch up on things. I've been out of this industry for a while, but it's super interesting. So that's my main motivation. And I'll give the microphone to Matteo from Calibro.
Hi, hello to everyone. I'm Matteo. My background is in design, communication design, and I'm interested in that workshop because beside my work, I'm part of a grassroots collective who is working on monitoring air quality in the city of Milano, and we are mainly using in situ sensors from ARPA, which is the main, which is the agency, the local agency for censoring and data air quality. And I was interested to understand how maybe to use both data from satellite and from in situ sensor to monitor air quality. And next one would be Andrea Benedict.
Hi everyone, I'm Andrea. I'm a PhD student in density design at Politecnico di Milano. I work with Angeles and I worked with Matteo. And I was interested in this specific workshop because I'm planning to work in a project that analyzes the state of water in the Aral Basin area. So it was quite fitting and super interesting to see that there was this workshop that introduced these concepts. And yeah, it will be amazing to work with all of you. And I'm going to pass the microphone to Antonio Policicchio.
Yeah, thank you. Hello, everyone. I'm Antonio. I'm member of the Artificial Intelligence Unit at NTT Data Italy. I'm actually a PhD in physics, and now I'm following some projects on air quality monitoring and carbon flux monitoring. So this workshop is really interesting for me. I would like now Francesco present himself.
Hello, everyone. I'm Francesco. I'm, as Antonio, I'm working for NTT Data Italy. I'm a data scientist working on computer vision application. In particular, we are interested in satellite images. We worked before on different scenarios, and this particular stream is really interesting. So the air pollution and climate monitoring. I also have a background in physics, and now I'm working as a data scientist. I switch to Luigi.
Hi everyone, I'm Luigi. I'm a developer at Dot. I also worked in the past as a PhD student and a postdoc in computer science with geographical data sets and geovisualization, and I still have an interest in the field. So I'm really interested in seeing how have we done this project with satellite datasets. So here I am, and I'm giving the microphone to Jib.
Hi everyone, I'm Jeep. I'm an interaction designer at OpenDot. So I'm a colleague with Daniele and Luigi. And so I have worked also on the same project as Daniele for months, but I don't really know what he did and how the magic happens. So that's why I'm here. I want to learn something. I will give the mic to Tan Nguyen.
Hello, good morning. I'm Tan. I'm a student in the action design in southern Germany, and I'm very curious about food crops and monitoring them and maybe giving predictions about what food is like very pricey in 10 years or something. Who else haven't talked yet? Maybe
There's Luca Feliciani, Luis Pimentel.
yeah, okay. Then Luis.
Hi everyone. My name is Luis. I'm living here in Milan. I'm an architect. I'm really curious about, let's say, like also traditional representation of cartography, and trying to somehow innovate in the way in which, let's say, architecture or also master plans and these kinds of elements can be represented. I was also really interested about it, especially because of I'm trying to see in which way we can, let's say, in our professional practice, try to gather the biggest amount of information and data in a way to, let's say, practically try to tackle all of these issues in architecture and urbanism. So yeah. I give the word to Julian.
Hello, everybody. Thanks for having me. Yeah, I'm from Germany. I'm information/communication designer. And I've been interested in dealing with satellite data for quite some time now in projects, mainly also on the brink of visual journalism. But besides that, I'm also very much interested in the theoretical aspect, like in how do we perceive satellite data? So kind of do we perceive it more as kind of a type of imagery or actual data sources? And also everything that's surrounding space junk and these kind of aspects. So I'm very much interested in the whole topic. And I would like to pass on to Simona.
Hello, everyone. Sorry for I don't have a webcam right now. And I'm also a colleague of Daniele and Luigi and Jeep from OpenDot. I see the amazing work they've done with satellite data before. And I'm interested in learning the basic of how to do that. And I hope I will work on some project with them in the future. And also interested in the artistic part of the artistic use of satellite images and data visualization in general. So now I let the microphone to Luca.
Hi, I am Luca. I work in a company in Rome and I want to start a team that works on geographical information system and satellite data. Then this is why I'm here in this course. Now I don't know who's the last one, probably Martina. No.
So Martina and OpenDot Fab Lab are
okay.
I didn't introduce them. They are from the organization behind the workshop. I guess there she is, Martina. You want to say something?
Hello. Hello, everyone. Hi, nice to meet you. And together with Christina, we're part of the organization team. So thank you for being here. And I hope you're going to enjoy this workshop. That's it.
Tiziano is also from OpenDot. Tiziano, you want to say something? You're the only one missing, actually, and Christina.
Hi. I needed to run back to my computer because I was listening from the other room, from the Fab Lab. And that's it. I'm really interested in because I'm a colleague of Daniele. I've seen the development of Math Museum, and I was really interested on how this satellite data can be used to see some specific aspect of geographical problem, like the fires and ice melting we have seen, but also some specific information we can gather about the city, like the work Calibro is doing in Milan. It's really interesting, and I want to follow that. Thank you.
All right, I'd say we listen to everybody, so let's move on. I'll share again the slides. Can you see the slides? Okay. Yeah, actually, it's cool to to see some of my colleagues here, but that's because we have very different profiles at times. So I'm a developer, there are designers, architects, makers. So an example, the reason why we are having this workshop is because of a project that we made with the scientific coordination of ESA, but we really had different tasks. So it's true what Jeep says. I don't know in detail what Jeep did, and she probably don't know what I did because the exhibition was so large and there were so many touch points that we had to split our work. But anyway, okay, let's move on. I would like to have a note on Earth observation data. It really is a very complex and heterogeneous field. You have different types of data. So today we will work mainly with raster data types because we will work with satellite imagery. But you also have vector data types. For example, you can have geographical political boundaries, you can have regions of interest or points of interest, and those are typically vectorial files or data formats. Then you have also tabular data types because you have metadata about the acquisitions, you have sensors that are not actually optical or they're not cameras, they just give you values that are more on a tabular type, like CSV and other formats. And there's lots of domain-specific technical knowledge. So that it deals with physics, with astronomy, with geography. So it's a really rich field, and it can be very complex to dive into it. So today, our perspective on this workshop is to give you just an introduction, because when we started doing this exhibition, we had to do the same. So I have a background as data scientist, but I never worked with Earth observation data. And at first I was very confused because there's lots of data that you can find, lots of sources, but you have to know what you need and how to get it. So this is let's say the focus for today, okay? To get access to the data and to do some very basic visualization. For more advanced topics like processing, these are very advanced and they are out of scope for today. Also note about the products. So Earth observation data is often divided into products, and there are different levels of these products. Level 0, which is not usually open to public, is the unprocessed but reconstructed acquisition of the instrument. So it's the raw acquisition of, in example, an optical sensor. And you had the payload data, and you may have communication artifacts. So this is a very rough kind of data that needs some processing. Then you have level 1, which is reconstructed data at full resolution, and you have some annotations. You have annotations about the time of acquisition and the coordinates of the acquisition. You can include radiometric and geometric calibration coefficients. So let's say that it's a more complete package to understand the data. And then you have level 2, and we will first see this kind of product, which is composed of derived geophysical variables at the same resolution of the original acquisition. So it means that, an example from a sensor, an infrared sensor on board of the satellites, we can get the land surface temperature, which is a derived variable. But you also, this data is in the original format. So you just see the portion of Earth that has been observed at that time by that satellite. And then you have level 3, and this is the easiest, I'd say, level to process, because these variables have been mapped on uniform time and space grid scales. So it means that you can ask for the land surface temperature for a particular day in a particular bounding box. Okay, so this is like querying a database, because all the computations and aggregation has been made by the processing units, and so they are ready to be queried as if it was a service, basically. And then you have level 4, which is modal output, so results from analysis, and we will not cover this today. So these data products are usually composed of one or more bands, which are the data itself, so the sensor values. An example for multispectral instruments, we could have the RGB bands, which are different frequencies. And the same terminology is used for non-spectral data. So we will see that for a level 2 product, the land surface temperature is a band, although it's not really a spectral feature, let's say. Then you have, of course, product metadata, so acquisition time, information about the source satellite, the position, the orbit, so all the data that can help you reconstruct the context of the data. And then you also have auxiliary data that is useful for processing. An example, the cloud probability associated to data. We will see that in detail right now. So this composition varies between satellite families, between the instruments on board of one same satellite, and of course with the product levels. So there's not a unified, let's say, structure. As I told you, we dived into this world because we made an exhibition in the Math Museum in Lisbon, which is called Art Beats. I will share you you should find the presentation on the package I asked you to download, and there are some links if you want to go in detail. And so this exhibition was, as I said, very large, composed of many different touch points or sub-exhibitions. The one that used Earth observation data is, sorry, this is a typo, Planet Pools, the last one, which is, let's say, a wallpaper projected on a very large monitor, on a very large wall. It's actually 14 meters wide. And this is a kind of contemplative exhibition, but at the same time, it wants to give information about the climate crisis and its causes and its consequences with as much as possible scientific validation. So, and that's where ESA really helped us, because ESA validated all of our outputs. Okay, so here's a video of the complete installation. I will go very quickly. Show you also because, as you say, it's a very wide format. It's not that easy on Zoom. So this is the introduction. You can see the globe with a texture which is not actually let's say the high resolution photo you are used to see, but it's a land cover layer. What does it mean? It means that for each pixel, you have the information about how that pixel is covered. So if there is vegetation, if it's covered by concrete, so it's an artificial land cover. You can have information about the type of vegetation. You can see if it's water, snow, permanent glacier, and so on. So it gives you pixel by pixel the information about what kind of soil you're looking at. And after this, okay, after this introduction, okay, it's going a bit slow for me. Can you hear me?
Yes.
Yes.
Okay. Sorry, because I see the video buffering and. Okay. No, I just wanted to let you see the installation. Okay, I will just go through the main features. So okay. Nope. Let's try again. What you see here is in the background, the entire globe covered with information about the land surface temperature. So how hot is the surface? And then you have a zoom on different cities. We took 7 cities, and we wanted to see the difference between the city center and the surroundings. So you see that the parts in violet are hotter actually than the surroundings, which are mostly non-urban surfaces, so vegetation. And in contrast, you see that the most central parts of the city are hotter. And this is a phenomenon which is called urban heat islands, and that's what we will see today. And going on, you also have the nitrogen dioxide concentrations for each of the cities. And you can see that it varies between cities. So in Mexico City, it's really evident. It's also evident in Tokyo. Usually also in Beijing, maybe going a bit, okay. In Beijing, you can see that it's massive in some days. And this is the second, actually the second topic that we will monitor. So let's start with urban heat islands. So as I said, the urban heat island occurs when a city experiences much warmer temperatures than nearby rural areas. Its causes are mostly the artificial surfaces that absorb solar radiations. And this compared with soil covered in vegetation, it's obviously let's say that it absorbs the radiation, so it also absorbs heat. While with vegetation, you have a much cooler surface, let's say, also for some biological phenomena. And then you also have waste heat, so traffic and every activity that generates heat in the urban context is a cause, obviously, of urban heat islands. This phenomenon is best observed at night and during summer or winter, and especially, obviously, in dry climates. And this phenomenon impacts on the microclimate of the city. So, an example, it extends the duration of wave heats in big cities. And it also acts on global climate because it obviously influences the urban power consumption, like the energy used for air conditioning, for refrigeration, and so on. So this is an issue that that has local consequences, but also global ones. So how can we monitor this phenomenon? We have two ways. We can monitor the air temperature, which is usually provided by weather stations. And the second approach that we will use today is by monitoring land surface temperature, which is, in this case, provided by satellite infrared imagery. So as I said, land surface temperature is the radiative skin temperature. What does this mean? Well, roughly it means how hot or cold the surface of the Earth would feel if you would touch it, okay? So you can expect that if you touch the area on a glacier, it's very cold surface. If you touch the area on a city, it would be hot. And that's a simple comparison just to understand what this variable is. And this metric is provided by the Sentinel-3 sea and land surface temperature radiometer. And this is provided as a level 2 product, so we will play around with it. The grid resolution of the acquisition is 1 kilometer by 1 kilometer. And this satellite has a full orbital cycle in 28 days. What does this mean? It means that if you start with an acquisition, let's say over Milan, you have to wait 28 days to have the same exact scene, okay? So the same exact position of the satellite and the same exact observation. This doesn't mean that you won't have data over Milan for 28 days because the satellites make many orbits around the globe in a day. And they are actually twin satellites, so they are two. It just means that if you want the same exact acquisition, then yes, you have to wait 28 days. This data is available as a near real-time resource. So it's available more or less after 3 hours on the acquisition, or you can get the non-time critical product, which is provided roughly after 24 hours for the acquisition. And the difference is that the non-time critical has some corrections about the orbit, so it's a bit more precise. Okay, and so Sentinel-3 will be our source, and for the processing we will use SNAP. So SNAP is a software platform that has been developed by ESA, especially for processing data of Sentinel-1, Sentinel-2, and Sentinel-3 missions. And its features are, well, you can display satellite imagery really fast and you can navigate through them. You can manage layers, so you can add more information on top of what you are interested in. You have, this is very important, you have accurate reprojection for common projection standards, and we will see it in detail later. Well, multi-threading and multi-core support if you have to do lots of processing. You have really lots of pre-made functions available to process the data. And last, you have a graph processing framework, which is essentially a way that lets you do batch processing. So you define a procedure and then you apply it to a number of products. Okay. All right. So enough with the words. Let's go in detail on practical workshop. And let's say the first thing we should do is to connect to Copernicus Sci-Hub. The address is scihub.copernicus.eu. This is the main page. You have the user guide, which has been quite useful for me. So if you have time, give it a read. And then you have these 4 sections, which are the main sections. The first one is the Open Hub, which is the graphical interface through which you access the data. The API Hub, which is the API interface if you want to access the data programmatically. Then there's a separate interface for Sentinel 5P data. And this one, I never really opened this one, so I can't tell you what this is about. I guess we will just go straight with the Open Hub. Okay. All right, so as Julika said, this is a visual interface to get our data and to do some filtering to get just what we need. So we have the search bar. We can save our search. Here we can choose between layers, but actually the only layer is OpenStreetMap, but it's fine, I'd say. You can switch between moving the map and selecting a region of interest. And then you have the account. Oh yeah, you should have an account. I made one for the workshop. Password is the same as the user, so DDMP workshop. But I suggest you to make an account since it's free and it's immediate. So why not? All right. So once we logged in, we can dive in searching something we're interested in. Sorry. Okay. If we press this menu here, you can open this. Sorry, my computer is really slow, doesn't like hot environments, and today in Milan is really hot. Anyway, here you have a section for filtering your research. So the first thing we could put is the sensing period. So we can define, let's see for the last week, the products that we can retrieve. So from 22 to 28. Then we can choose the mission. So we say that we would start with Sentinel 3. So we check it. Here we can select if the products will be the source of the product will be satellite 3A or B. Remember, they're twins. We can also just leave it blank and it will take both. And what we want to get is as we said, the LST, so the land surface temperature as a product level 2. So this is what we are interested in. This 2 means level 2. LST is the name of the variable. Okay. We can also choose the timeliness. So if it's near real time or non-time critical, there's also this short time critical, but I don't know if it's valid for Sentinel-3. And we can also have some more, okay, we can also define here the level, but it's not necessary since we defined in the product type, and the relative orbit start, but I guess it's not an information we are interested in. So if we make a search, it will actually look for all of the acquisition for Sentinel-3A and B in that period worldwide. And as you can imagine, it's a lot of products. It's actually 6,651. So a bit too much, I'd say. But the interesting thing is for each page, so we are seeing 25 products, and we can see the locations of the products. And if we see one in detail, just random, we click on the eye. And here you have more information about, so you have the data summary, the footprint, the information about orbit, sensing start and stop, the instrument that was used. So lots of metadata that you may find useful to filter out your products. Okay. So let's say that I want to filter a bit my request because actually it's pretty much huge. And let's say we want to define a region around Milan. Okay. What can I do is to make this square. And sorry, close this. The filtering is okay. It's just the same, but I this time define the region of interest. So let me search again, and this time we should get definitely less products. So yeah, so it's 21. Okay, and take care. These we define this region of interest, and these products are all the products intersecting this region of interest. They are not containing the region of interest. This is very important because if you want to have a full analysis of this region, you don't want the acquisition to intersect it. You want to contain it. And to have this kind of query, you have to do some more advanced query on the search criteria bar here. You can check it on the guide. But essentially, go to advanced search. Okay. Yeah, my computer is definitely not happy today. Okay. Anyway, here you can have more information on how to do more complex searches. Basically, you have to say that you want to make a search that contains a region of interest, and that region of interest must be specified as a well-known text format, which is kind of GeoJSON if you're used to work with GeoJSON. Okay, so it's you define some points or a polygon or a line by selecting their coordinates. Okay. All right, so from here, you can download your data by pressing this button. So you can select the ones that you prefer and just click on the download, or you can add them to a cart. If you add them to a cart, then you can download a bulk download file, which is in metaphor format, and you can use a download manager that reads this kind of file to download all the products that you selected. Okay. So for this workshop, I already downloaded 2 products about Milan. that you can find in the package that I included. One is taken in the morning, if I don't remember, it's about 9, and the second one is 9 in the evening. So I'd say let's open Snap and let's play around with them. And let's also see how much time my computer will spend in starting Snap. Did everyone download Snap? Are you executing it? Did you have any problems, anyone?
No problem. I downloaded and it's running okay.
Great. Mine is still loading. Okay, in the meanwhile, I will show you how a product is done once you download it. All right. So these are the two products that I downloaded. The name is you download them as zip, so you just have to unzip them. You can see that it's a folder with a very long name. It's just lots of information about the acquisition. So Sentinel 3A, the level 2 LST product. This is the acquisition time. I guess this is the ingestion time, but I'm not sure, or maybe the end of the acquisition time. Ingestion time and other stuff. I don't really remember because it's very long and it's not really that interesting. What's interesting is the content of the folder, which is a series of NC files, and then a manifest, an XML manifest, which is actually the file that we will open with Snap. So hopefully, yeah, it should be up. Okay, so we can open it with the dialog window. Hello. Okay, let's do it this way. Oh, no. Sorry. Okay, he will think a bit. It's processing the information. Okay. And now we have the products imported into Snap. You see that here we have many folders. The one about metadata is exactly, well, it's the information we saw on open access, which I guess is this one, the metadata section, same information. And then you have also lots of other very technical specific information. So we're not really going to dive into this today. Instead, we are going to what we're really interested about, which is the bands of the products, right? You can see that in the bands folder, there's lots of stuff. We expected maybe just LST, but as I told you, the products have also auxiliary data, and this is the case. So let's first check the LST. So if we double click, we open the visualization. We'll think a bit about it and then, okay. And the first thing you will notice is that it's upside down, let's say. And that is because when taking this acquisition, the orbit was, the satellite orbit was descending. So that's why we see it upside down. If we want to have a quick view in the right direction, just to, I don't know, make it a bit clearer, we can use this wheel on the interface. And okay, there it is. And you can see some strange things, let's say. So these black areas, which means they're really cold, they're actually obviously turbulences, they're clouds, okay? Because this type of acquisition is influenced by the cloud coverage. So yeah, we'll have to deal with it. Maybe not in this workshop, but if, in example, you have to do a time series monitoring allocation, then sooner or later you will end up with a region that is covered by clouds, and you'll have to deal. You have to deal with it. We also have, as I said, auxiliary data. We can check the biome example. And this is the land cover I was telling you about before. So you see that pixel by pixel, we have a different color. This is Milan. And if you go to color manipulation, you see that this color corresponds to artificial surface, right? It's this one. And obviously this violet is water. This is the Garda Lake. While on the vegetation, you have the kind of vegetation. So broad-leaved evergreen forest, closed middle-leaved forest, and so on. You can also see LST and biome side by side. If you go in navigation, you have to check these two, and then, and then you click on this icon, and you will see them side by side. And the nice thing is that it will sync the operation that you do with your mouse. Okay. All right. So first things first. Here we're not understanding much, or at least, okay, it's clear that here in the Alps we have colder temperatures. We kind of expected it, as well as here in the central Italy, which is a very, it's mountains, okay? But if we want to have a more, let's say, informative look, we can apply a color map. So if you go to color manipulation and click on basic, you can select a color map. We can, for example, take the first. And you can see that now it's a bit clearer. What we can do also is to set the display range. And we can decide to get the range from data. This is actually temperature in Kelvin degrees, okay? And now there's something coming out, right? So we can see that in the zone near Milan, we have a black spot. This is maybe Turin. And so you see how darker the urban areas are. And if we have some other European cities, maybe no, there's cloud over Paris, but in other positions, you can clearly see Paris as a black spot, okay? So what if we want to get an acquisition of maybe just the area of Milan, and we want to save it as an image? The first thing to do is to reproject our scene, because this coordinate reference system is not the one that we are used to deal with. It's actually a coordinate reference system that is that derives straight from the satellite acquisition. If you go to world map, you can see the area that we are covering. This is really useful. So I was saying we have to transform this this image in a coordinate reference system that is more useful for us. Let's say that maybe we want to overlay it to a Google Maps layer. The two layers should obviously fit one over the other. And in order to do this, we have to make a reprojection. So we will start by using one of our operators. We are applying it to the raster data in our product. And you can find it in geometric and reprojection. As I said, there are lots of operators. You can do lots of stuff, even some machine learning. You see unsupervised classification, supervised classification, principal component analysis. These are all techniques that maybe data scientists know a bit, and they are included. We will stick with very easy operations. So reprojection. Okay, so this dialog window is asking us what's the source product. Okay, it's this one. The target product, because it will be saved as a separate product. You can choose the format. Beam DMAP is the format used by SNAP. So it's by default this one. You will see that we will also work a lot with GeoTIFF, big TIFF, which is essentially a raster data type containing just the information that we need plus the coordinate reference systems and the coordinates of the acquisition. It's asking us where to put this. I will just put it in the desktop. It's okay, maybe with a more nice name. Okay, so let's say the acquisition time and reprojected. Okay, let's run it. You will see that it is not a very light operation. It will take time to do this kind of computation because it is actually reprojecting all the raster information. Oh, sorry, I didn't select the reprojection parameters. And of course, SNAP is blocked. Did you succeed in reprojecting? Anyone? Still going on?
I am still doing it.
Okay. I just finished. So you can see that it's now, and there's a new product in the Product Explorer window. And here in the bands, I have all the bands I had before, but this time, let me close the biome. This time, if we open it, we will see that it's quite different, right? So you see that the proportion are different. Let me just take the one. Tell you the truth, we had to also choose the reprojection parameters because we had to choose the coordinate reference system that we want. There are lots to choose from. If you don't have to overlay it on a web layer, you could go well with UTM WGS84 automatic. But if you want to overlay it on, let's say, a Google Maps layer, then you should get a particular coordinate reference system, which is I don't remember it, sorry, I'm going to read it. Or if anyone knows it, please. 3857. Okay, pseudo-Mercator. And this is the coordinate reference system that is usually used by services as Google Maps, Bing Maps, Mapbox, and so on. Okay, so once you select this, you can leave this other information. You can choose a no data value. So you see that in example, you have no information about water because water surface temperature is processed separately. It's a separate product because it needs other kind of computations. And actually, it's not provided by ESA, but it's provided by a partner, which is EUMETSAT. And so for these no data values, you can specify none, not a number, or you can insert like -9999, and then when you process it, you know that you have to look for this value to process the no data values. Okay. All right, so now what we want to do is to cut a square over Milan because we just want that portion. And to do this, we have another operation, which is, so let me first make sure that I'm operating on the correct product. So I want this one. We go to raster and we go to subset. So subset essentially lets you take just a portion of your data, both in terms of coordinates, than in terms of data itself. So let's begin with the spatial subset. We can insert pixel coordinates about our scene, or we can select geo coordinates. Now in your package, you should find a file that it's named Milan chords, if I'm not wrong. Sorry. Yeah, Milan coordinates. And here you can see, thanks Tiziano. Tiziano has come to cool my computer. That's really appreciated. Okay. And this is a bounding box I pre-computed for you in terms of coordinates. So you have longitude and latitude pairs. So what you can do in SNAP is to insert this value. So we should insert north and south latitude and west and east latitude. Sorry, longitude. And I just copy paste it. So, okay, so all these decimal numbers are not really necessary. I'd say that 3 are more than enough. But anyway. Then put. Okay. Okay, so you see that we now have a very small square around Milan. So our spatial subset has been set up. We want also to take a band subset. So right now we have everything selected, which is a bit too much. We don't need all of this information. I mean, for our scopes, they obviously have a purpose, but since we are making just a very, very easy visualization of LST, we don't need them. So we can just select none and we get on the LST. And also in the, you can see that the size is very, very small because we are taking a very, very small portion of our product. And in the metadata subset, yeah, you can't really do anything. So, okay, let's see. Yeah, it's telling me that if I didn't check some options and I won't be able to create bitmask overlays, but we don't really care about this. So I don't want to. Okay, now you should have another product, which is called subset 0 of, well, the first one. And if we go to the bands list, now we only have LST. And it's more or less a square, it's a rectangle, let's say, around Milan. Okay, this is the zone we covered, right? And now we can apply some color manipulations. So we select our bands and we can take the range from data. And now we can clearly see that there's a spot in the city center, right? It's clearly visible. And this is an acquisition that has been made in the evening, so 21. And I'd say that it's pretty evident, right? If you wish, you want to play a bit with the values of the color manipulation. If you go to sliders, you can select the position on the value scales in order to adjust your visualization, and you have an histogram with the values that you find on the image. And you can, of course, select the color map that you like. You can also, I guess you can also write new ones or save custom presets. And here you can insert specific minimum and maximum values in Kelvin degrees. Okay, so let's say we want to save this image. Actually, the quickest option is to right-click, go to Export View as Image, and okay, you will see this panel, which is asking you some things to select. So which image region? You can save the view region, which is this entire rectangle with also the dark gray background, or you can just select the full scene, which is probably what we want. And then we can select the resolution of the image. So right now, our full resolution is 110 pixel per 80 pixel, which is a bit, I don't know, delusionary. But we can rescale it, so we can say. So to be clear, that this is the resolution of the data itself. We effectively have 110 per 80 pixels because those are the values that we cut from our bigger acquisition. So here we are just rescaling, okay? But the squares will be exactly 110 per 80. All right, we save it as our output, wherever you want. Put it in the desktop, and then you will find it as an image. Will I? Yes. And that's it. Okay, so this is just a visualization of the LST, of the land surface temperature values. And it's a rough visualization of urban heat islands. If you want to do something more, I'd say, complete, something more sound from a scientific point of view, I suggest you to follow a tutorial that I put in. You will find a file in the package that is called Useful Links. Yeah, and here you have this ESA webinar on LST and urban heat islands. Actually, this procedure I made is the start of that workshop. Basically, what they do, so they follow by selecting the temperature in some points around the city, which are rural areas. So let's say 10 points around here. Then they take some points inside the city, and they compute the mean temperature outside and the mean temperature inside, so that they have more or less the offset range in degrees of the temperature. It's not a difficult, it's not at all difficult. So you can easily do that, and the tutorial is quite good. So I suggest you to follow it if you're interested. Last thing before having a small pause, I would like to let you see the graph builder. So we said that SNAP includes a tool that lets you do some batch processing. Okay, so you define a procedure and then you put some products and it apply the procedure to all the products you select. So you can access it by clicking here. It opens up this interface. So here you have your graph, which is by now composed of a read and write blocks. To do the same procedure we did, we should choose, we said, raster, geometric, reproject, and raster subset. Then you, with the, you can make your links, or you can even, if you click with the right click, you can automatically connect the graph and you can save it. And then I didn't use, sorry, I never used this interface because once saved this graph, let's say, yeah, my graph.xml, I can close this and I can open this other interface, which is batch processing. And here I select my graph. So yeah. And you see that here now you have all the operations that we inserted before, so reproject, subset, and write. And you select the products. Here we should have input. We have to select the XML file, okay? Okay, and once we selected at least one product, we can populate all the requirements we have to insert for our processors. So the coordinate reference system that we want, the subset that we want. So we select the source bands, and again, we select the geographic coordinates, or sorry. The navigating is not very easy. Okay, you got the procedure right. Or you can sub-select a pixel region, and then in the write you just have to define, well, same as before. So the name, the format, and the folder in which you want your objects, your output. All right, so this was an introduction to SNAP. We made a very simple task. Actually, an optimization of this procedure, since you saw that for the first product, the initial transformation was quite, it took like 20 seconds, which is not that much. But if you want to do that for 1,000 images, then it starts being an issue, right? So what you can do instead is to make a first subset with a bigger area, let's say around the Po Valley. Then you reproject just that portion of the original acquisition. And then finally, you do the final subset focusing over Milan. Okay, it's just a way to spare some seconds of computations that multiplied by lots of products becomes minutes and maybe hours. And okay, so I'd say that we can, are there any questions? Is it all clear? You have any doubts, anything you would like to ask for this part?
I have a question. Is there a way to know the measure unit of the image of the map I'm visualizing? I guess here we have Kelvin, right?
Yes, here we have Kelvin.
If I don't know exactly what the pixel intensity means, where can I find this information?
I guess it's here somewhere. So position here. Okay.
I guess maybe I should know it before downloading the product.
No, but it's for sure here around this metadata. Would be nice to have a search, but I actually never. Temperature summary. Currency reference. I'm sure that it's around here somewhere.
Okay.
I just knew that it was Kelvin, and I went ahead with Kelvin, but it's in the metadata.
Okay.
Let me just search for other 1 minute and then I stop. I'm curious now. Okay, here in the measurement accuracy, you have this K, which stands for Kelvin, but it's not really the entire information. But from here, you can say that it's Kelvin. But yeah, I guess it's around here in one of those infinite metadata.
Okay, thank you.
Any other questions? Okay, so I guess it's time for a small pause. I'd say 10 minutes, and then we will get on with doing more or less the same procedure that we made right now, but with code. Okay, so see you in 10 minutes, so 11:40. Okay, let's get back to the workshop. You still there?
Yes.
Great.
Yes.
Good, good, good. I didn't check the Zoom chat, but Judica put a link providing all information about the Sentinel missions. So when you have doubts, like the one that Simone had before, you can also check the website, and there will be useful information for all the data products that are provided by Open Access. All right, so let's also switch back to our presentation. Good. So let's move on. What I would like to show you now is the exact same procedure, but this time made with code. A question that someone may ask, especially people not expert in coding, is why use code? We have a wonderful software, Snap, that also has batch processing utilities. So I think I have everything, and it's true. But coding has some advantages. In first place, you have more freedom in developing your own processing routines, because you have a wide set of operators in Snap, but maybe you have something really custom, and then your best choice is to code it. Okay. And also you have access to more sophisticated tools. For example, if you want to implement some deep learning with I don't know, PyTorch, or yeah, any framework for machine learning implementing neural networks. So your best choice is again to use code. The thing the reason why we use code is actually to automate this entire process and to let it scale on hundreds of products, and also to make a procedure that would run automatically. So let's say we have to update the exhibitions. We don't want to reopen Snap, select the products on which process for which use the graph processing tool. We just run some code and you're done. And actually, I found out that some tasks can be easier, at least if you're confident with code. Okay, so if you know how to do things, and the things we will do are pretty easy, then you will actually spend much less time in your work. And why Python? Why we decided to use Python? The first obvious reason is that it's widely used. It's a very used language, especially in the scientific domain. Many of you will already know this. And as a consequence, there are lots of libraries and plugins and frameworks for this domain. So you have Numpy, Matplotlib, scikit-learn, lots of libraries that help you in developing your process. And it's easy to learn. It's actually much easier than compiled languages like C, C++, etc. It's not the best in performance. It's not the fastest language you can use, but it's a good compromise. And of course, because we love it, we use it a lot at ... for many different applications. And sometimes the tool you're most confident with is always the best tool. I would like to use Anaconda for this workshop. Maybe some of you already know it. It is basically a distribution of Python and also R for who's into statistics, but mainly Python. And Anaconda is made to simplify the package management, so installation of libraries and plugins. We'll see that it's not really always straightforward, but it's easier than using just command lines. And it also provides self-contained Python environment. It means that you can have a Python environment with a specific version like 2.7 because maybe you need a specific library that is just supported by that specific version. But then on the side, you can have a completely separated Python environment with another version with other libraries installed. So they are self-contained, safe environments to do your computations. You can also install related software like IDEs, so the place where you actually, the editor in which you write code, data management platforms, et cetera, et cetera. So I guess that more experienced people with Python will already have their environments, but if you're a novice, if you never used Python, or if you don't know how to handle the libraries, Anaconda is the best choice. Another thing that we will use is the SNAP graph processing tool, which is exactly what we saw before. So the graph processing framework, so the blocks we built before, but invoked by command line. So they are essentially the same exact operations, but instead of selecting them from a graphical interface, you can run them as a command line. So as a process. There's also a Python library, which is called the Snappy, which is more or less the same. It lets you use operators directly in Python, but I found easier to use the command line processes, also because then you can integrate in other languages. Let's say you are coding in JavaScript, you can follow more or less the same procedure and just recall the command line process. So this entire structure allows us to do everything we did before in code. Let's recap a bit the process. We downloaded the products from Open Access Hub. We unzipped them. And then we had these three operations. Well, we saw just reproject and subset, but I was telling before that it's okay to have a first subset just to have a more quick iteration on the reproject phase. And then we write the output file. We will do just the same with Python, and we will use some libraries. So Sentinel Stat is a Python library for downloading products from the Sci-Hub API platform. The unzip process is not really that interesting, but you can use it, a Python library just to stay in the, let's say, in the Python environment. Then we will apply the same operators, but this time using GPT as subprocess. And then we will write the output file with our, let's say, we will personalize our output by selecting a color map, an example, and the image size with these libraries. Okay. So let's start Anaconda first. I don't know if you had the chance to already set up an environment. Is there anyone that still doesn't have a full environment? Because we sent some instructions, but maybe they are, I don't know, it's better if I make a quick overview of what is needed, right? Starting Anaconda. Did anyone already use Anaconda?
Yes.
No.
No.
Okay, so let's go into this. My computer is still opening it. You should open it from, if you have Windows, you choose just Anaconda Navigator. Okay. Can you see the window, the Anaconda Navigator window?
Yep.
Yes.
Yes.
Okay. So this is the home page where you have some software that you can launch or install if not all the software are already installed. So you can choose what to install and what not. And these are the environments I was telling you before. So you start with a base environment, depending on the version that you downloaded, it should start with a specific version of Python, just to be sure that everything is fine. And because I found, let's say, a good match between the libraries that we will use and the Python version, I will create a new one. It's called, I don't know, workshop, if you wish. You want Python, and for this tutorial, we will use 3.6 version, which is a bit outdated. Well, yeah, not the most recent, but that's because this way the installation of libraries is much easier. So let's create this environment. It will think about it. It will download some stuff, and it will set up. There will be like 1 minute, 2 minutes of processing. So is there anybody who is that already had this Python environment without Anaconda maybe?
Yes, I'm trying to do like that.
Okay. Yeah, I decided to use Anaconda also because some of the libraries that we will use are not really straightforward to install. And while Anaconda lets you install them in a relatively easy way.
In my case, I don't really have the opportunity to select any previous versions of Python in Anaconda, but I already checked for the libraries that you recommended in the email, so they are all installed, if that's fine, I guess.
Okay, okay, great. Okay, so this is our environment. You can see, if you check the installed, you can see that there's already some stuff. So Python with its version, pip, which is a package manager, and other stuff, which I'm not going to see in detail. What we want to see now is install what we need. So we will search for packages. First thing first, the package we will need the most is Numpy. Numpy is a library for vector and matrix computation, and it's widely used in data science. So we just select it, and then we will select all the libraries we need and then go ahead. So along with Numpy, we maybe use Matplotlib, which is a tool to show graphs and images. Check it. Then we will use Pillow. Pillow derives from PIL, which is the Python image library. So it's used for operations on images. Select it. And we will also use OpenCV, which is a very complete library for computer vision. We will just use a very simple function, but otherwise it's a very complete library to make analysis on images and videos. and then raster IO. Okay. So these are the libraries we need, I guess. Yeah, that should be everything. So we apply. Think about it a bit. This is basically solving package specifications. So it's making sure that all the versions between the libraries I requested and their dependencies, which are these ones, are okay. So we apply. There will be other 2 minutes, let's say. This also depends on your connection speed because it's downloading the packages and then installing them in the environment. Okay, while it installs the library, I can also go in home. You can see that now the applications refer to our environment, which is grayed out because it's installing packages. The next thing you will do once it's over is to also install Spider if you wish to use it. Otherwise, if you use other IDEs like Visual Studio Code or Sublime Text or I don't know, there are many, feel free to use them. Okay, I will use Spider because it has some nice interactive console in which you can see the status of your variables, see what's inside, and so it's a nice tool for situations like this. Okay, it's over. So we now install Spider. It's almost over. Has anyone finished installing it? All right, I'll wait another minute, then maybe we go forward. I hope that someone of you already finished.
Not yet.
Not yet. Come on. All right, while this goes on, you can also make another thing, which is install another library that you won't find in Anaconda Navigator, which is Sentinel SAT, which is the utility to download our products. To do so, you can go in the, I have Windows, but it should be more or less the same. If you go in the Anaconda menu, you should have an Anaconda prompt. Okay, and if you click on Anaconda prompt, you will have this command line, and what we will do is to use pip to install Sentinel SAT. To do this, you should first switch to our environment, which is called workshop. Actually, yeah, let's do this. Activate workshop. We press enter, and now you see that on the left you have workshop. It means that we are using that environment. Okay, and now that we are here, we can write pip install Sentinel SAT. So this is telling pip, which is the Python package manager, to install this library. It's telling me stuff about their dependencies, which are already satisfied. And then you should read successfully installed lots of stuff and Sentinel SAT. Okay. Is anyone having problems? And meanwhile, my spider has finished, so I hope yours too. I actually had already it open, so we can just open it. This is Spider. So this is the window where you write code. This is the console where you read your output, and you can also write interactively your commands. And this is a useful variable explorer. So when you run a script, you can see here in a graphical interface the values that you computed. Okay. Okay, so let's start with the first task, which is to download data from the Sci-Hub using the you have my username and password on the script. Okay. Let's open this first script. Sorry, I'll open it from scratch. We go to open, then we go in the folder of our package. We go to LST Python, and we open 01 downloads sci-hub.py. Okay, here we are. I guess all of you already had a look at Python, more or less know how it works, but okay, the operations will be really, really simple. So this is just some metadata about this file, the author and how it was created. And the sentences here, actually this is not needed, and this neither. What we see here is some import, because what we do when we write a Python script is to import the libraries that we need. So you see that now we are going to use Sentinel SAT, and you can import Sentinel SAT by importing this module. So from the Sentinel SAT package, we are importing Sentinel API. We're also importing the date module from the datetime library, even if I think we will not really use it. And then what we have here, we have a variable which is called output dir, and this is a string. So this is the folder where we want our products to be downloaded. Okay. Then we have two variables that are called Big Milan WKT and Milan WKT. And these are just the bounding boxes for the Milan area that we want to analyze. So this is bigger. Actually, you can find it in the Milan coordinates. If you see here, I put bounding box of 100 per 100 kilometer in well-known text format, which is the format I was telling you before, more or less like GeoJSON, maybe a bit more compact. And this is a wider area, it's the double, so it's 200 per 200 kilometers, always in WKT format. So basically, these two variables just contains this exact string, right? Okay. And then there is a variable, not useful right now. We'll see it later. Okay, so the first sentence is to initialize our Sentinel API object. The Sentinel API object is an interface for the API of ESA Sci-Hub, right? And you saw that in open access, you had to log in to download the products. And here we are doing exactly the same stuff. So this is my username. This is my password. And I'm declaring that I want to take data from this URL, from this endpoint. This is the default, but in example, if you want to download water temperature instead of land temperature, then you should put the EUMETSAT URL that you can find on their website. And there are also mirror websites where you can download data from. So this is just the main one, okay? And this is the initialization. So it will connect to our service using this username and this password. Then what we want to do with this object that we named API is to make a query. Our query, the first argument of the query is the geographical area that we want to use as a zone of interest. In this case, we are getting the bigger area around Milan. So Big Milan BKT, right? This is the first parameter. The second parameter is our date range. So we're getting products between 21 and 28 of June. And this is declared as a tuple, which is more or less an array. It just has round parentheses instead of square parentheses, but okay, it's just these two dates. Then we can define the timeliness exactly as in the interface. So we want non-time critical products. This is a very important field, area relation. It means you see that before we took just the products that intersected our area, and instead maybe we are interested in products that cover that fully cover our data. So this string is telling the API object to query only for products that contains our region of interest. And then we, of course, have to specify the product type. So what are we going to download? And as we said before from the interface, we want the level 2 land surface temperature product, okay? These values match exactly the same on the interface, okay? You didn't see this one, but I guess this is the only one that is not matched in the interface. The other ones are more or less the same that you will insert in your interface. So let me comment just the last line, and let's press play and see what happens when we make such a query. So hit play. We'll think about it. Oh, nice. Invalid username or password. DBMP workshop. Really? Because it's maybe lowercase. Yes. Okay, it's over. Didn't download anything, but if you go to Variable Explorer, you should see something like this. So these are all the variables that we wrote in our script, and these are the values. So this is a Sentinel API object, this is a string, this is another string. Also, our output here is a string. And we have the products, which is an ordered dict. It means it's a dictionary, but it maintains the order in which the objects are inserted. If we double click on it, we have this interface, which is telling us exactly the results of the query. So this is just an identifier. And for each identifier, there is an object, which is telling us basically the same metadata that we found in the open access interface. So begin position, creation date, the file name, the footprint, the ingestion date. Okay, so and the interesting stuff here is that until you download your products, you can filter out this list. Okay, so let's say that you just want to get the the acquisitions taken during the morning. It's not something that you can do in the API, but you can filter out this with a short function, and you can get only the morning acquisitions. Okay. So once we checked out this list and we think it's okay, we can uncomment this line, which is telling us, so which is telling the API object to download all the products, to put them in this output directory, which is the one that we specified here, and the maximum number of attempts to get the file, because the file could be missing or there could be connection problems. So after 2 attempts, it just stops asking for the file. Notice that the Sci-Hub API has a usage quota limit. You can download at most 2 products simultaneously per user. So if we click play now, hopefully, all right. Unsupported operation error creating stream. Oh, this looks like a connection error. Yeah. Did you manage to download the data by running the script?
I have the same error.
Okay.
I got another error,
which
says progress not found. Please update Jupyter.
Oh yes, that's a silly issue on Spider. The thing you can do, you can open the Anaconda prompt, and you can do to the folder of the workshop. So CD and reach your folder. Should be this was. Let's see. The commands may change between operating systems.
Okay.
You reach LST Python. And you can launch the exact same Python procedure by writing Python and the name of the file. So 01 underscore download sci-hub.
Okay.
And if you go here, okay, it's downloading now.
I'll try.
But yeah, there's, okay, this is a connection problem.
Yeah, same error here.
Yeah, it's the same error that we had here too.
Yeah, me too.
Okay, so it can happen, and it happened in the past. So, and this is also the reason why I included a second script, which is called 01B download Creodias. I'm not going to use it now, also because you have to install another dependency. The thing is that instead of using the Sci-Hub ESA service, you can use the Creodias service. So Creodias is a private company that is fundamentally getting all the data from ESA, storing it, and it's providing it for free to their users. So you have to create a Creodias account, and then you can access their API. They're obviously, they are no profit. So what they sell is computing environments to make your own algorithms based on data. So it's like if you have your own cloud, which is already connected to the data sets. And so you don't have to download all the stuff on your computer. You just use their cloud and let the data out there. But APIs are free to use, and it also has a more permissive quota limit, so 10 concurrent download, if I'm not wrong. But you have to install this library, which is called TurSpy. I'm not going into detail there because it was just an alternate, a backup, let's say, for you if you wouldn't succeed with Sentinel API. And that's also why I provided to download the data set that we will use. It's in LST Python downloaded. Okay. So once you download these products, well, of course, you have to unzip it. We will quickly do that by interface, but it's trivial to do that in Python. For now, we will just call a folder called unzipped, at the same level of downloaded. And then this. I use 7-zip for this. Extract files. Yeah. Okay. Should go. Okay. See if we have Peter last now. Okay, let me check also. Okay, so our structure now is that we had our downloaded products here. And then at the same level, we have the unzipped folder in which we have the products in their folders with their contents. Yeah, I'm sorry for this part. Actually, I had problems yesterday too, and that's why I included this one. If you want to use it, remember to install Torfy, otherwise it won't go. Okay. And the thing you have to change are your user and your path. And then we have our region of interest, which is Big Milan WKT, with the VKT of the big area. And then this is the query. We want products from the Sentinel tree. This is the starting date and the ending date of the query. This is the kind of product and the timeliness. It's more or less, it's very similar to the Sentinel SAT interface. Okay, so let's suppose that our downloads actually went fine and we had our unzipped folder filled with our products. What we want to do now is to take the same steps that we took with SNAP. So we have to subset, reproject, and subset again. So we bring here the same information about the areas, so the bigger one and the smaller one. And we also have this PSG. So if you remember, this is the coordinate reference system. Yeah, maybe this is more recognizable. And this is the value of coordinate reference systems that identifies the web Mercator, so the projection that is used by Google and companies. All right, so for each image now, we have to do the same procedure, right? So the first thing we do is to get every entry in the folder unzipped. So this is a for cycle that tells us to scan this directory and to get every element inside that directory. If the current entry, so this procedure will be repeated for every directory inside this folder, right? Because this is a for cycle. So for each one, if the entry is a directory, which is what we expect, because we expect to have this inside the unzipped folder, then what we want to do is, first of all, to get a more censored name, because this is an example of the folder names, right? But it's huge. We may want something more compact. So what I'm going to do here is to split the name of the entry with respect to this sequence of characters, which is this one. So basically what I'm doing here is I'm taking this part of the name and this part of the name as two separate strings. So let's do this. If I put come on. Ah, it's here. Okay. Now, what I'm doing now is I'm putting a breakpoint so that when the code gets executed, it actually stops here. Okay, so we see that we have entry, and here we can write entry.name, and this is our string, right? It's something like that. So if I do entry.name.split and I put the 4 underscore, what I get, let me use a variable. So results equal, let's check what result is. So result is an array, which is composed of the first part and the second part. So I just split over this symbol. Then what I do is to get the satellite, because you see that the first information is S3A, is the Sentinel 3A. So I'm taking the first chunk of split name, which is our result. So if I write result, let's make something even better. Split name equals, so we have the same name. So split name is exactly this. So if we do split name 0, we have just this part. If we do split name 0, 0, 2.3, we are getting the characters composing that string from position 0 to position 3 excluded. So it's S3A. And you can also avoid this, because by default, this will be 0. It's the same, okay? So here I'm telling to get this information. We also need the timestamp. So timestamp equal to split name 1. And now in timestamp, we have exactly this part. We split this according to an underscore. Sorry. And we take the first chunk. Sorry. And we should get the date if I'm not. Oh, because there's this one. Oh, that's because I missed. Yeah, I missed the. Oh. I missed an underscore here, so now it's here and it's splitting over this. Okay, sorry. Let me do a quick trick. Okay, this is now the date. It's exactly what we have here inside. And finally, the full name of our resulting image would be what we stored in date plus what we stored in sat. So it will be this underscore S3A, right? Which is the name of the satellite. And that's how we will name our our final files. Okay, so this was just a funny way to have a proper name for our files, actually. Now what we need is our XML. Remember that we were scanning every folder. Now we have to get every XML in each folder. So it's our path plus the XML address. And okay, we just print something just to make sure that the full name is correct and that the inf file is correct. And then finally, we have this part that will process our initial level 2 product with subset, reproject, and subset again. So you can see that we are calling a process that is called GPT. And this GPT is exactly what I was telling you before. So it's the command line utility to recall the operators. If I go here in my Anaconda prompt and I write GPT, you will see a big waterfall of information after a while. Oh, come on. Is it working for you?
Excuse me, what package will install a GPT?
It's installed by default with Snap. It's a Snap utility. It's not a Python. So when you install Snap Desktop, it will ship with GPT.
Doesn't work for me, but I will check it out.
Is any other one experiencing problem with GPT?
When I try to run the script, it tells me that subset is an unknown command.
Same to me.
Here in subset.run. So you already run this.
Yeah.
Okay, so let's.
And if I try to type GPT in the terminal, it doesn't give me back all this list of options, but just one line.
Yeah, me too.
What operating system are you on?
macOS.
And?
Same macOS.
I'm on Ubuntu, and the installation of Snap Desktop actually doesn't install GPT. So now.
That's nice to know. Really?
I guess so, because I don't have GPT as a command line installed. So I'm trying to install it separately.
Let's make something. If you do GPT -H, you should have an help.
I tried, but with no success.
So it won't display anything of this information?
I think that GPT is also another utility for macOS, like disk utility. And that's maybe what's happening.
Yeah, probably.
You can do maybe which GPT and find the recall GPT from its folder. Maybe. Sorry, guys. I tried just for Windows. Didn't expect to have this kind of problems on macOS.
So it should be part of the Snap package. So
it should be part of the Snap package, maybe.
Let's see if. Okay, so maybe I can execute it directly from the folder of Snap.
Yeah. Yeah.
Instead,
if you find the binary, you can do so.
Yeah. So the binary, I mean, I don't know who else has macOS, but if you just go in application, Snap folder, bin folder, there is also a GPT executable file, and I'll try to see if it works.
Yeah, if you try to launch it and it gives you this stuff, we're okay.
Ciao.
What you can also do is GPT name of the operator, so subset -h, and it will give you help for the specific operator.
Yeah, I mean, the file from the Snap folder is working, I mean, and now I have just to find a way to update the Python code to use the...
Yeah, you just have to include before GPT the folder, which is not the best option, but it should work.
Should work, okay, we'll try.
Okay. So meanwhile, if we ask help for a specific operator, so GPT subset -h, we are asking for help for the subset operator. And here you see the description, so create a spatial and or spectral subset of a data product. And then we have some options. We will just use some of these options because we don't need these kind of details. We will just specify the source file, and then we will ask the subset of operator to not include the metadata, which is what we were doing also in the interface. We will select a georegion, and we will provide our WKT as a geometry file. And we will also tell it to get just the LST source band, right? Because we don't need biome and DVI, et cetera. We just need LST. And finally, the other two variables are not strictly for the subset operator, but they are general for the GPT command line, which is the format, the output format of the file. And we want also the target file. So we are saying that we want a geotiff and that we want it in the subset one folder with this name. And this name is exactly what we computed before. So S3A underscore date and time. How's it going with macOS?
Fine, the script is working, seems to work.
Okay, okay, good. So this is the first operation, so first subset. Then we have the reproject. Remember that we renamed this from PSG to GRS, so we should recall it. GRS. This is the reproject operation. So again, we define the source. This time, if we ask for help on the reproject, should tell you about the parameters. We will just use source again, the PCRS, which is the text specifying the target coordinate reference system. And then we will also specify no data value. Remember what I was highlighting before in SNAP. This is the exact same operation, and we will put minus 9999 as a no data value. And again, data format and timestamp, and sorry, the output folder. And finally, the subset again, which is again subset with the same parameters we put before, but now instead of big Milan, we are putting Milan because we want to get the final box restricted on just the inner square around Milan. Okay, so I'll put, since I already have computed this, I will add some live just to differentiate from what you already have in your folders. Blah, blah, blah. So subset 1, 5. Then we have subset 2 live. Okay. And then we have reprojected live, right? Reprojected live. Okay. So let's run this script. This is Python 02 subset reproject, and hopefully, if everything is fine, we should see the operation. So it's starting with subset. This stuff is all GPT internal strings. You just don't care about it. Is it working for you?
Yes, it's running.
Yeah.
Okay, and it's filling the folders?
Yes, it's updating the images that were
okay.
already there, I think.
All right.
Yeah.
Okay. So it now should reproject. Ah, yes. I also have to rename this. Name. Okay, sorry about the confusion. Is it working for everyone?
Yes.
So what we should get is here in the subset 1, the first subset. You can't actually see them since they are geotiffs, and the operating system doesn't know, at least for Windows, doesn't know how to show these images. Then in the reprojected, you should have you should have the reprojected ones, and then in subset 2, you should have the final cut of the reprojected image. Sorry, I made a bit of confusion on these steps. Is everything clear? the procedure. So this part was just to get the final name of our images. This part is to make the operations on the images.
Clear.
All right. So then, now that we have this, what we want now is to take our final processed output, which is in subset 2. It is in GeoTIFF format. We want it in a more usable format. So let's say PNG. And this is exactly what this third script is doing. So, sorry, I have to go a bit quick because we're running out of time. So these are the libraries that are being imported. And here I'm getting all the TIFF images that are inside this folder, subset 2. Now that I have this list, I can cycle through it. So for each file, I can, well, print the file name, and I can open this file with raster.io. So we imported it as Rio just for brevity. And what we are doing here is to open each file and read its product. Maybe we can make a breakpoint somewhere here. And okay, we should have data, yes. So our file is none other than the name of the first file. We are opening it and we are reading its data. Notice that in source, we have some information like the width of the image, the height of the image, and we also have the bounds, the geographic bounds, but they are not expressed in decimal degrees. They are expressed in meters with respect to our coordinate reference system. So if we write source.crs, we know that our CRS is 3857. We can have a transformation in order to read it as latitude and longitude in decimal degrees. There should be a function that is called the transform bounds, which is also from raster.io. Then we can look inside the bands, or at least get the indexes. So if we write source.indexes, we see that there is just one band, which is LST. And what we are doing is we are reading it. And if we see data, let's do it after. Yeah. So another step that I'm making here. Right? Another step that I'm making here is to remove all the invalid values. You remember that I replaced not a number with -999. So what I'm making with this operation is to apply a mask to our matrix. So this is a function of Numpy. The original data is here. We read it from here, and we apply this mask by specifying the value we want to mask. And then finally, we can show our image with plot.show. And if we press play here, we should have a nice, hopefully. Yes, okay. So finally, we visualize something. This is our first image, right? We removed, if any, the non-data values, and we visualize. So this is what we need, okay? We need to save this image. But right now, it is stored as a Numpy array. So the following things we are going to do is to convert it to an image. It's not as straightforward. You see that there are some lines. So the first thing to do is take the minimum value and the maximum value of this matrix and clamp it to 0 and 255. This means that if the minimum is, I don't know, minus 10 degrees, and the maximum is 40 degrees, this range will be shifted and rescaled to a range between 0 and 255. Okay, so we are just, in a way, normalizing the values of our data in order to respect this range. And we're doing it with respect to the minimum and the maximum. Then what we are doing is to transform the value data type as unsigned integer at 8-bit. It means that every value in our data is effectively between 0 and 255. And right now we have all the values we need in the range we need. We also need to create a mask because we want the image to have a mask for the null values. And to do this, I'm taking the old value. So this is the original data, and I'm telling it for each value, if the value is greater or equal than 0, then automatically put it to 255. While if it is less than 0, then it's 0. What does this mean? This is our opacity layer. It's a mask, so it's basically an alpha channel. So what I'm telling it is every value greater than 0 should have full opacity. Every value less than 0 should have no opacity. And right now, the only values having no opacity are these ones. Okay, so I'm effectively putting at 0 opacity the none values. And I'm creating a different image just as I did here. So there are two separate images, one with the actual values and one is a mask for the opacity. Right, so we know that the data is actually in, it's just an array of values, while we know that an image is created by 3 channels, RGB. So here we are just saying multiply by 3 our matrix in order to have 1 per color channel. So from the black and white, we now have 3 arrays, 1 for the red channel, 1 for the green, and 1 for the blue. They have all the same values. We will actively instead apply a color map with this line. You have a list of color maps you can probably see by pressing Control space. No, it's not suggesting anything. Is it suggesting to you some values to put here? Okay. Not important. We'll use this color map.
Yes, if I type color, but I'm on another text editor.
Okay. Oh, now it's working. Okay, it was just thinking about it. So here are the color maps depending on the Python version and the OpenCV version. You could have more than this. I will select this one. These parentheses are wrong. Okay. And we have to do this operation because by default, Python applies this color map inverted. So we're inverting the channels from BGR to RGB. We're almost there. We finally, now that we have 3 channels, RG and B, we can create an image. So we're telling to store in the in variable an image object and to take the data from this array. We are doing the same with our mask. So these are, again, 2 separate images. One is the actual values, RGB, and one is the opacity layer. And this is to put the 2 together. So we are applying an alpha mask to our image. Right. So what we also want to do is to have a size of the image of 600 pixels, at least for the horizontal value. So we can get the size of the image and the first element, which is the width, and divide it by 600, which is the value that we want. And this is more or less an upsample factor. So we know that multiplying the actual width of the image by this, we get 600. So here we apply a resize for the width and the height. So this is the height because this is the first element of size, width. This is the second element of size, height. We're multiplying by the upscale factor. And we get a name from the previous file name just by getting characters from position 8 to position 27. And finally, we are done. So if we try to press play, and if I didn't do any mistake, no such file or directory. Where does it say? Is it working for you?
Same error.
Same error? Let's see. No such file.
For me, it opens a small windows with the preview of the image.
Just one, but then gives you an error, right?
I don't know. Still thinking. I think no error yet.
It should be real quick. I guess it's. Let's see. It's something with this name. This is probably not correct. Sorry. I think we have to shift 1, 2, 3.
Maybe there is a slash after underscore 2.
It was this index was wrong. Now you see that you have all the images have been processed with the same technique. And if you go to our output folder, hopefully you should have something like this. Okay. So these are our images. And what you can see here is that in some, it's very clear where the city is, and you can see that the temperature is effectively more intense in the city center, here, here, here. And there are some other cases where you have cloud coverage, like here. Okay, this is a big cloud over Milan. So this is actually something you have to deal with. And you have different strategies. You may just cherry pick the image you want and select those that are without cloud cover, or there are more advanced, let's say, techniques based on temporal reconstruction. So you have a temporal series and you have more or less a mean value derived from your temporal series, or you have spatial reconstruction. So you take the value of the nearest pixels, which of course works only for small not good areas. Or you have the combination of both. You can use spatial and temporal aggregation to fill the holes. Okay. All right.
But for example, I have a question. The first image in the folder, how do I read it? What does it mean? That there are a lot of clouds, or is correct? Or
yeah, this is totally correct, and this is just lots of clouds over Milan of this particular shape. You can see that there is more or less a yellow brighter spot here, but it's not really evident because there's a cloud layer that is not. So in this case, the urban highland effect is not visible. And it may happen in this case that it's fully covered. Okay, so it depends on the quality of your observation. What we did actually to have a video that is a sequence of let's say a temporal series of the temperature of Milan is to aggregate, to take the mean values for every pixel in order to build a single day. So if I want to show the temperature for this day, I aggregate this. Let's say the past 10 images. Take the complete mean, and then if you get the mean of enough samples, you should have a reasonably filtered out image showing showing the urban highland effect. But this technique is widely used. We will see later with the final example that we will do the same for nitrogen dioxide.
Okay, thank you.
All right. So let's get back to the presentation. Okay, last argument, very quick, sorry. Nitrogen dioxide is, as Julika was saying, a pollutant. It's not directly a greenhouse gas. However, it is responsible for the creation of greenhouse gases. And these kind of gases, so nitrogen dioxide, they enter the atmosphere as a result of anthropogenic activities and natural processes. But the percentage is higher on the anthropogenic activities. And these are the sources. So as natural sources, we have volcanoes, lightnings, and fires, basically everything that is relating to combustion, okay? While for the artificial sources, we have fossil fuel plants, so gas and carbon fuel plants. We have fuel combustion, so traffic is actually one of the major sources of nitrogen dioxide in the atmosphere. Household activities such as heaters, especially gas or wood heaters, and agricultural soils, because there are some fertilizers that are based on nitrogen dioxide. So this is also a source of this gas. Okay, this is more or less the same video that Julika showed you before. Maybe you have seen it. It's the pre and post-COVID nitrogen dioxide concentration in Italy, and you can see a big drop, mainly because of the traffic and the lowering of urban activities. I'll skip this, sorry. And in this case, so we want to check this kind of data from for Milan. And in this case, data is coming from the Sentinel 5P and especially from the tropospheric monitoring instrument, which is called abbreviated as TROPONI. This is also provided as a level 2 product. The grid resolution is much coarser. It's 3.5 per 5.5 kilometers. But the interesting thing is that it is also available on Google Earth Engine, and on Google Earth Engine it is available as a level 3 product. So this is very convenient because we can spare lots of computation, and we will see that it's much easier to get the data. So Google Earth Engine is a Google platform for Earth observation data. What does it provide? First, a data platform. So it's a huge repository of Earth observation data coming from a wide range of missions, both from NASA and ESA. And it also has lots of historical data. And it is also a computational platform. So it means that basically you write your own routines by writing code, and you can perform those not on your computer, not on your machine, but on the Google infrastructure. And so you can work with very, very complex, cumbersome tasks and on very, very large data sets. Obviously, it means that you will send your procedure. It will be processed in the Google infrastructure, and you will get back the results. But you won't have control over the time it elapsed and other stuff. So it's a kind of black box. Okay. So what we will use today is the web editor to write code. We'll use JavaScript, but there's also a set of APIs to access the same functionalities directly from your language. So maybe Python or JavaScript. There are also some requirements and limits. So you need, of course, a Google account, and you must require access. So they must validate your request. It is free for research, education, and non-profit use, but you may not sell data products generated with Earth Engine. And you won't find all the data products from the satellite. So an example, the LST level 2 product that we use now, is not available in Google Earth Engine. And there are also API quota limits, but I guess that who's interested can, they are quite complex, so you can see in detail on the Google Earth Engine website. Also, yeah, we will see very, very basic JavaScript. There's a documentation here stating some common differences between Python and JavaScript, but I'd say that they are really not necessary now. So let's go straight to code. Okay, so here you can see the main page, and the first thing you should check out is the datasets. Datasets are subdivided into topics and also into missions. So here you have a very exhaustive number of topics. You see that there's the Sentinel section over here, and you can also browse them by tags. So if you here write, I don't know, wind, you find the tag and you see that there are 15 data sets. So we're interested in Sentinel collections. Sentinel-3 is the one we saw before, but there's just the ALCHI instrument. There's no SLSTR instrument. But there's the Tropom instrument. So it means that we can open this section. And here you can find all the products that are delivered by Google Earth Engine with respect to Sentinel-5P. We have aerosol index, the cloud coverage itself, carbon monoxide, formaldehyde, nitrogen dioxide, which is the one we will see, ozone, which is a greenhouse gas, and sulfur dioxide and methane. So let's select nitrogen dioxide. Sorry, let me get back 1 second. If you see here, you have offline or near real time. What is changing is, as in the case of before, it's the dataset availability. In the case of near real time, we have 2 days ago, while for the offline, we have the 20th of June, okay? So if you go ahead, you have the description of what the dataset provides, and you have a more specific bands description. So these are exactly the bands that we saw before in the SNAP software. And we see that these are the values we are interested in. So the column number density, but also the tropospheric and the stratospheric column number density. So this is just the density, the concentration of nitrogen dioxide at different heights, at different layers of the atmosphere. So the atmosphere is divided in layers. The tropospheric is the nearest to the surface, and the stratospheric is the second one. We'll get this value today. The thing that I particularly like and that allows you to really explore every data set in really a short amount of time is this small script. It's like a hello world for the specific data set that they provide for every, almost for every data set. And if you open it in the code editor, sorry, this is the part where you require a Google account. So if you didn't manage to have a Google account approved for this part, you won't be able to access the code editor, but I will show you. Okay, so this is some pre-made code for this specific dataset. Just a quick look at the interface. Here you have your scripts that you can save. This is more or less, well, these are Git repositories, okay? So this is a repo and this is a file inside my repository, okay? So for who's using Git, you know that you can version your scripts. This is the code editing window. You can get the link for your code. Okay, you can run your script and you can reset the view. And here you have an inspector to inspect the layers you have on your map, a console, and tasks that are, we will see it later, it's just procedure you send to the server side. Okay, so this is our hello world for tropospheric NO2 column number density. So let's run it. Okay, so without writing a line of code, I can have a quick overview of what we can see, what we can observe with this with this data set. Yeah, every time you move, not if you move, but if you zoom, it recomputes the tiles for the visualization. And this is our visualization for nitrogen dioxide. You can see some spots. So this should be Paris, I guess, and this should be Milan, probably. Yeah, this is Milan. You can see how there's a clear spot in the concentration of nitrogen dioxide. And you can also see particular very, very high concentrations in China, in the big cities. This is arguably the zone where you can see most concentration of this gas. All right. So this is just a quick overview. I will also just go through the code very, very quickly. We are getting an image collection from this data set, which is the offline, so Copernicus, Sentinel 5P offline, level 3 NO2. And from this image collection, we select the band tropospheric NO2 column number density. And then we filter the dates that we want to see. This is interesting because here we are not seeing a time slider. So you see that there are 5 days here. And the fact is that the image you see is actually the computed mean over time of the data set. So what you're seeing is the mean of 6 days of NO2. And this is done by just getting your time interval and here adding a layer to the map with the mean of this collection. So you take the collection and you compute the mean. Then you can specify how you want it to be visualized. You can modify the palette. In example, you can also, I don't know, use just 3 colors or 4 colors. And you, sorry, nope. And if I run it again, okay, you see that now the spots are even clearer thanks to this color map. See that in India there's also high concentration. And you can see that the entire Po Valley is very polluted, especially because then you can make the comparison with the Alps, which are relatively not anthropized, so not so polluted. Okay, so what we want to do is to take just an area around Milan and visualize it. And to do so, you can specify some hotspots. Okay, that are called the geometries. And okay, we'll see how to use it in the script that I prepared, which does exactly the same thing, but it doesn't visualize anything on map because we want to download the files, and we just want this portion. We don't want the entire world. Yeah, abandon the changes. Okay, so this is our script. It's very simple. We select the start date and the end date. This is not important really. What we want to have is a sequence of images. More or less what we wanted to do before, but with the smoothing filter we were talking about. So we want to take an image for each day of the week which is the mean of 10 or 20 images, so that we have very smooth values and we don't have cloud coverage that goes through the image. So for each day that we want, we compute our initial date, which is the effective date we want to start with. We will compute the day, which is 20 days later the start. So our end interval, which is, so if this is 1st of June, this will be 21 of June, okay? And we do just the same that we did before. So we take the collection, we select our band, we filter the date according to what we just computed. So in our example, 1st of June, 21st of June. And we now add this function, which enables us to filter geographically our data set. So we're just taking the Milan area. The Milan area is defined here, and you can define with your mouse, or you can write down in GeoJSON your coordinates. We compute the mean, just as we did in the example before. And then just to give a title to our image, we take the date, so 1st of June, and we get it as a string with year, month, and day. This string getInfo, it's just a function that transforms this data object into a string. It's getInfo because our data object is an Earth Engine object. And if you have Earth Engine object, so everything starting with EE is a function that is recalled by the server. So you're not computing it on your machine. This goes in the cloud platform to be computed. So when you call getInfo, you are requesting information about this object, and it will, in this case, it will return it with a string. And finally, we can export our image. And here, the thing is that since you're not computing locally, you don't know when the computation will be finished. So you cannot just click and download. You have to wait for it to finish, and then you can choose where to save it. So in this, you can have 3 options, if I'm not wrong. The first one is to save it to your Drive folder, so the Google Drive account that is linked to your Google account. You can save it to Google Storage, which is something related to Google Cloud, or you can save it in your assets here, but it will stay here in your Google Earth Engine environment. Okay, so I have chosen to export my image to Drive. I have to specify what I want, what's the image that I want to export, and we said that we want our mean. We need a description, and for this, the title is more than okay, and also this file name prefix. The folder is where you are going to save your results. This is, if you remember, is the coordinate reference system. This is, again, the region of interest. I think it's not really needed since you filtered the bounds, geographical bounds here, but just make sure. And this is the dimensions that you wish to get. What you're getting here, it's not a PNG or a JPEG, but a TIFF in this case. So if we run this script, you have all the things that we put in the print. But the important thing is that now we have a tasks list. And what does this mean? It means that when you When you recall this function, you say it to the Google server to instantiate these tasks. Okay, so these are the computations needed by Google Platform to give you the image that you need. And they do not start by themselves, but you have to run them. Okay, so if you click on run, there's this window that asks you some more things that you already brought here in the specification of the export. So you can just run them. You can make the same for everything. And the result, if I go to my drive now, it will take approximately for this simple calculation from 1 minute to 5 minutes, more or less. But if I go to my drive now, I already pre-computed this stuff. So you see that I have my TIFF images already here. So you basically have to wait for these activities to finish. It will become blue as this one that I made yesterday. Or if it fails, red. Failed, or if you stop them. I stopped this, so they have been stopped manually. Right. So what you have in the end is more or less what we had before. So a GeoTIFF with our raster layer. And what we want to do is to save them to an image. And for this, there's a script in Python, which is more or less the same that I wrote for the LSD. It's inside NO2GEE, and it's called NO2 TIFF to PNG. The only different things that I'm doing here is to have these images computed for 2 cities and not just one. So I'm computing it for Milan and for Paris. Because if you see, we have two regions of interest defined. Okay, so if you change here Milan with Paris, you change it here, and maybe you rename the folder destination, you can do the same extraction for Paris. And what I wanted to show you, but we don't have time, unfortunately, is to have images that can be used as to see how to see the images of one city and on the other, and to see how they differ in terms of NO2 concentrations. And the only thing that is different from the first script is that you have to do the same procedure for both cities, and that instead of taking the minimum and maximum from the TIFF itself, you compute a global minimum and maximum so that you can compare the 2 cities, because otherwise every city will have its own minimum and maximum, and they would not be comparable. So the result of the scripts is these 2 image sets. If you go to material NO2GE, we have PNGs Milan and PNG Paris. And you can see I'm cycling through the images. They are changing very slowly because we have this smoothing filter over 20 days. So there is no sudden change in the concentration of nitrogen dioxide. And this, of course, depends on the amount of days that you use as filter. And we could see it side by side, maybe. Oh, Windows. think. No. Oh, no, it's this. Sorry. Everything that is. And you can see that in this period, in this particular period, the concentrations of NO2s are higher in Paris. Okay, and you can also see that Milan has this. The images about Milan have this kind of star, this subtle star, and I guess that these are the roads, so the high-speed roads that go towards Turin and towards Bologna. So you can see how the traffic shapes the concentrations of NO2. All right, so sorry for this second part, which has been a bit rushed. I didn't expect to have this kind of issues. I just, well, thank you for participating and for making it through here. And be sure to follow us on Instagram and Facebook, or to stay updated about the following workshop. And so the next workshop, just as a recap, are the 24th of September, the Sound of Temperature, which will be about data sonification by our awesome Nicola. And then the 6th of October, Data Speaks, visualizing ways to raise awareness, which instead could be about data visualization, and Michele will be the person that will keep the workshop. All right, so do you have any questions? Or comments or doubts?
A lot of, but I think I will keep it for myself and then.
No, you can write us.
Yeah.
You can write, I'll put my mail on the chat. Okay. So yeah, if you have any issues, if you want to know more about specific things that we saw, or I don't know, you have some problems with the scripts, and I'll be glad to help. Okay.
Okay. Thank you.
Thanks, Daniel. Thank you very much.
Thank you, Daniela.
Okay, so I'll wait you for the next workshops, and thank you and goodbye.
Thank you very much.
Bye, thank you.
Ciao, grazie. Bellissimo.
Bye.
Ciao.
Ciao.